In this video, we're going to talk about inverse functions. So when you think inverse, think opposite. So question, which functions are able to be undone or reversed or find the opposite so that the outputs take us back to the inputs? And then we want the result to still be a function. Okay, so this is the whole idea of an inverse function. Normally, with a regular function, you have a domain, which is your inputs, and a range, which is your outputs. And so the function takes you from domain values to range values. You plug in 0, you get out 3. Plug in 1, you get out 0, and so on. So f is a function since every input corresponds to exactly one output. So this is just talking about function first. Now we're going to get ready to talk about the opposite or the inverse function. Things switch. If you think opposite, now what was the domain is now the range. What was the range is now the domain. And so f inverse takes what was our range values and basically maps them back to the inputs. So f inverse is also a function since every input goes back to exactly one output. So domain, range. Okay, look at this example here. First, think about it. Is this one a function or not? I have plugged in 1, I got out 0. Plugged in 4, got out 0. Yes, that's still a function. That's still okay. Remember my vending machine example a while back? If you plug in or put in some money, you type in a code, you'll get your snack. This is just like maybe another form of money. Maybe my snack cost $1. I put in $1 bill, I got out my snack. Or maybe I put in 4 quarters and I got my snack. So this is still a function. Now let's see if we do the inverse. Okay. Well, 0 has to map back to both of its inputs, 1 and 4. And so this is not a function. Okay, it's not a function when you're trying to consider the input and then 2 outputs come out. Okay, so let's make this clear. In this form, when 2 separate inputs gave us the same output, that was perfectly fine. But what's the problem is when one input gives us 2 outputs. This is like my vending machine where I put in one amount of money, but I got 2 snacks out. I typed in 1 code for my snack, but 2 fell out. So that's not a function. So now, what must be true of an original function to guarantee that the reversing process produces a function? The answer is that the function must be what's called 1-to-1. So each different input determines a different output. You plug in one number, only one number comes out, and you don't see that number again for any other input. So another way to say it, every output can't come from more than one input. So here's a graph of a function, and here's this horizontal line. This line, notice how many times at each stage as it goes up and down, it touched the graph. Okay? It only touched the graph once at every point. So once here, once here, once here, and so on. Even though right here in the middle it looks like it might touch more than once, if I zoomed in, this is not really flat. Okay? So the horizontal line test says the following. If every horizontal line that intersects or touches our graph of our function does so exactly once, then the function is 1-to-1. So this is a test for us to figure out, is the function we're working with 1-to-1? And this is. So I'll just take a couple points. When I plug in 1 into this function, I get out 1. Okay? And nowhere else on the graph will I ever get out the number 1. It only happens right there at that point. Let me draw the point for us. So I'll only see the output 1 right there. Never going to happen again. The output of 6 is never going to happen again, only right there when I plug in something a little less than 2. Okay? So every output on my y-axis only comes from one point on the graph corresponding to one value on the x-axis. Okay, how about this one? do you think that this function is 1 to 1? Well, let's see. Let's consider the horizontal line test. Look at this horizontal line as it moves up and down. Does it only touch the graph at one point always? No. So this one's not a function because when we started drawing horizontal lines, let's go ahead and draw one. Hopefully this is kind of straight. Not perfect, but not horrible. Okay, look at how many times this touched the graph. Once right here, once right here, once right here. So this output value, this looks like I picked around 2.5. 2.5 comes out of our function 3 different times. It comes out for some number right over here, like negative 1.9 maybe. If I plug in something right here, I think that might be like negative 0.4 roughly. And then over here, right, plugging in like 2.1 maybe. This same output came out of the graph 3 times out of the function. So that's not 1 to 1. And so what's going on and why we care about this is that if the function's not 1 to 1, it doesn't have an inverse. Because if I said, let's go backwards, hey everyone, I have a function, the output was 2.5. What was the input? Well, we can argue about it. Some of you might say this number, some of you might say this one, and some of you might say this one. So this is not 1 to 1, so we can't go backwards. There isn't an inverse. But this other graph, we can go backwards. If I said, hey everyone, if my output was 6, what was the input? Well, you would look at the graph, you would say, okay, here's when y was 6, so the input must have been somewhere right here, like maybe 1.8. Okay, so that's the significance of what it means to be a 1-to-1 function. So it appears in the prior mapping that for a 1-to-1 function, the domain of the original, so notice it just says f, the domain of the original function f is the range of the inverse function. And the range of the original function is the domain of the inverse function. Okay, so everything switches. If you just remember that things swap, they become the opposite. That's the whole idea here. What used to be the input, the domain, is now the range. Okay, we call it the range. What used to be the output or the range is now the input, the domain, when we're talking about the inverse function, when we're trying to go backwards. And so in general, we used to have that x gets plugged in, y comes out. And so now we think of y getting plugged in and x coming out. The inverse of a function, so here's our definition. If f is a 1-to-1 function, so this has to be true. So everything we basically just talked about was just so I can say this part of the sentence. If f is a 1-to-1 function consisting of ordered pairs, plug in x, get out y, then the inverse of f, denoted like this, and notice how I'm going to read this. I'm going to read this as f inverse of x. So even though it looks like f to the little negative 1 power, you don't read it like that. You say f inverse. So f inverse of x is the 1-to-1 function consisting of ordered pairs. Plug in y, you get out x. So the inverse function, you plug in what used to come out, and then the result is the original input. So to form the inverse of a function, f, we simply interchange the coordinates of each ordered pair that determines the original function. This is just a way of saying swap x and y. So f inverse is a function with this notation, what we just talked about, f inverse of x. And then just a note about the notation, this little negative 1, don't think of it as a negative exponent. It's just a notation. It's notation for inverse. So when you see this in the future on something like f like this, you would just read it as inverse. So to find the equation of the inverse of a function, f, we must recognize the following relationship. F of x equals y was what we've been working with before. This is our regular function notation. Implies that f inverse of y takes us back to x. Okay, so I know it's a lot of math notation, but the concept is really straightforward if you just remember that things are switching. We used to plug in x and we would get out y. So the inverse, we plug in y and we get out x. If a 1-to-1 function takes an input x, to an output y, then its inverse function has the reverse effect. So example, find the inverse of the function f of x equals 2x minus 6 if it exists. Okay, so everything we talked about so far was getting us ready to be able to answer this kind of question. So now the question becomes, well, how do I find the inverse function? How do I find the function that's the opposite of this one? And so first we have to verify, is this function even one-to-one? So check that it's one-to-one. If you conclude that it's not, you can just be done with the question. You'd say, oh, the function's not one-to-one, it doesn't have an inverse, and you're done. So first you check if it's one-to-one. So is this function one-to-one? And if you think about the graph of this function, okay, if you need to, you can graph it. Just think of f of x as y. You could say y equals 2x minus 6, and this is just going to be a line. Okay, this is going to be like a slanted line. If you remember, let's write this real quick. Your slope-intercept form of a line. So we have y as f of x, and the slope is 2. Oh, sorry for my writing here. I'm using my mouse. So this is 2 times x, and then this minus 6 in the back would be our y-intercept, where we would hit our y-axis. So we would hit the y-axis at -6. Let me just draw a really quick sketch. Let's change the color of the graph. We're going to say that we hit the y-axis at -6, and then our slope is 2, so we rise 2, up 2, and we run 1. We plot a point. Rise 2, run 1, plot a point, and so on. So this is just a slanted line, and it will pass the horizontal line test. Every one number for x that you plug in, only one y number is going to come out. So now that you've verified that the function is in fact one-to-one, you can move forward and you can start finding the opposite function, the inverse. So what you're going to do in step 2 here is really just a rewriting thing. It's going to make the rest of the work easier. When you see f of x, just write y. Okay, so that's just to make it easier. So y equals 2x minus 6. Now here's the main step. This is where you remember that inverse means that you're switching, you're doing the opposite. So you're going to swap or interchange x and y. So in your function right here, switch x and y. So where there was a y, put x. Where there was an x, put y. All right. Now, this is the answer, but we don't leave it in this form. So even though this is the inverse function, this is exactly the opposite of this function we had before. You tend to not ever leave it like this. We don't write it in this format because we usually solve for y, and then we have to put our function notation back on. Just like this originally said f of x, we're going to have to put our f inverse of x. So the main step is done. What you're going to do now is just do a little bit of algebra, solving for y. Okay? So here's y. So just think about the steps you would need to isolate it. You have to move this -6 and this 2. So you're just going to add 6 to both sides of this equation and divide by 2. All right, and there's y. Y is isolated. So this is a better form of our inverse function. And then you can even make it a little bit better by go ahead and saying x over 2 is 1/2 x, and then 6 over 2 is 3. Now, the last step is really similar to step 2. It's just a rewriting kind of step. You want to put your function notation back on. So you want to rewrite y in a more meaningful way. Don't leave it as y. Write it as f inverse of x. This makes it really clear that this is the inverse function of the original function that was named f. So if I know my original function was named f, this is my inverse of f function. And that's how you find an inverse function. So now, let's see what we have here. We have our function machine, f. We input x normally, and then what comes out is f of x, or y. So then the inverse of that, let's see what happens. Think about it before I show you. If you plug in the output into the inverse, okay? If I plug in the output into the inverse, it's asking the question, okay, here's what it came out. Inverse, well, what was inputted? Okay, I know it looks a little funny, but think about what the answer is going to be here. So the reason why we learn inverses after composition of functions is because of this step right here. Okay, so composition of functions is required in order to understand what this is asking you. This is saying that you plugged in one function, f of x, into another function, f inverse of x. Did you see that this was going to be our output? I hope you did, because we were just doing the opposite. We were undoing what came out of the function. Originally, we plug in x, we get out f of x. So if we do the inverse, we plug in f of x, and we get out x. So this is a fact that's going to help us verify inverse functions. Whenever you take the original output and you go backwards, you plug it into the inverse function, you will always get x as the result, the original input. Okay, and then this is the other way to write it. Notice this is actually the opposite of what this says as far as things getting switched. This is saying f on the outside, f inverse on the inside. So this is a really useful fact that says if you compose a function with its inverse in any order, the function can be on the outside, the inverse can be on the inside, or inverse can be on the outside, the function can be on the inside. Either way you do it, you're basically undoing what's happening, and you get back to the original input of x. So in the future, a function and its inverse, when you compose them anytime, it's always going to give you x. So let's prove this. We just found the inverse of f of x equals 2x minus 6. We figured out that it was 1/2 x plus 3. So let's just make sure we're correct, and we're going to verify. Okay, so we're going to compose these functions with each other. So we're going to do f composed of f inverse. So remember what this says. What we're going to do is we're going to replace our original, our input, what's in the parentheses here with what this says, f inverse. So what's in the parentheses, f inverse of x equals 1/2 x plus 3. So we're just going to plug that right into the parentheses. Then, think about it. F of something, remember what this means, f of something goes right into this spot for x. F of x equals 2x minus 6, so f of 1/2 x plus 3 equals 2 times 1/2 x plus 3 minus 6. So this is what we discussed in the composition video. Anytime you have f of some quantity like this, some expression, all of this right here, it just takes the place of where x was originally. And then from here, you just simplify. So distribute the 2, and then simplify, and you get x. And that's what we were expecting, but we proved it. Okay. Let's try it this way. Oh, this is a little smushed here, but hopefully you can still see it. F inverse of 2x minus 6. Okay, so that's the original f of x is getting plugged into the inverse. Okay, so that's going to get plugged in right into this x. We're taking the original function and we are plugging it into the inverse function right in this spot. So we have 1/2 times the original function, 2x minus 6 plus 3, and then we just simplify. So distribute the 1/2. We get x minus 3 plus 3, which is x. So we verified this again. And this is what's going to happen every single time you compose a function and its inverse. They undo each other, and then you get back to the original input of x. So how are the points a, b on the original function, f of x, related to the points b, a on the inverse function's graph? Okay, so we found an inverse function, we verified it using composition. Now we're talking about how does the graph look. Okay, so here's some points from a function. Okay, now look at these points. If my original points, let's pick one, 1, 2, were from my function f of x, look at what comes out of the inverse, 2, 1. If my original points on the graph were -5, -3, look what the inverse graph has on it, -3, -5. everything switches. X and Y swap. The original graph had a -1, -1, and because those numbers are the same when you switch them, that point actually stays the same. When you graph a function and its inverse, your graphs will reflect across this line right here. This line is y equals x. It's like a mirror line is what I like to think of it as. If I draw this line diagonally through my coordinate system, with y equals x, so this is the line where 1, 1, 2, 2, 3, 3 lie on this line. Anytime I draw that line and then I graph a function, my inverse function will reflect right across it. So notice your reflection. This is like a mirror. This point is mirrored over here. This point is mirrored over here and mirrored over there. So any point where the x coordinate is the same as the y coordinate will be on both graphs. So just like this one. And it's because it ends up being on that line, that mirror line, that line of reflection. So the graphs of f of x and its inverse of f of x, are mirror images across the line y equals x, that diagonal line. So how about this one? Okay, first of all, verify it's a one-to-one function. If you start to just like envision horizontal lines going across the screen, it only touches once. Even right here, it might look like it touches more than once, but this is really not flat. It's just that we need to zoom in more to see that this is not flat. So this is one-to-one. So let's think about the inverse of the blue graph. Well, here's our mirror line, y equals x. So before I show you, think if you can picture it in your head what the inverse graph would look like. Okay, so we have a comma b as a point on our original graph. So b comma a would reflect across that mirror line. Okay, this point over here would reflect across down here. These points that actually lie on our mirror line, y equals x, those points are going to stay the same. So I can just mark those. Those are going to stay the same on both graphs. And there it is. The green is the inverse of the blue. And they map very nicely across that line. They mirror. Okay, so the green is the mirror image of the blue graph. And therefore it is the inverse graph from our original.